Okay, let's start. So we started to look at multi-stage OTAs, and there we saw that we have a multi-order system. So we decided to look at the stability, and for the system to be stable, where do you want the closed loop poles to lie? Left half of S-plane, and because of that we decided to look at the root locus plot. Although this was slightly intuitive to plot, and it gives how the closed loop poles vary as you change the DC gain A0. Although it gives this plot, if you had designed your system for a particular DC gain, to find where exactly the closed loop poles lie on the root locus, it requires more calculation. It says how the poles vary as you vary the DC gain, but for a particular value of DC gain, it is not trivial. You need to do more calculations. So that's what makes it impractical, and so we try to understand stability through Bode plot. And in the last class, if you remember, we saw to make any comments about the stability, you first find the unity loop gain frequency and then find what is the phase of the loop gain at this unity loop gain frequency, and as long as it doesn't exceed minus 180, it is fine, and that made us define phase margin as 180 minus mod of this, right? So if this is 0, we will say that the system is stable, right? And also the second takeaway I want to have from the root locus discussion is the following. So if you recollect, if the loop gain had 2 poles, if the if the open loop or the loop gain has 2 poles, the root locus did something like this, right? And the moment I introduced a left half plane 0, what happened? So one had to fall here and other had to go here. So this was making the closed loop response more stable. Similarly, we also saw where if we had, let us say, 3 poles, so without doing anything, one would do this and one would do this, but when we added 2 zeros, one basically went here and the other, right? So essentially, if you didn't have these zeros here, the closed loop poles would have entered the right half plane, but the act of adding this left half plane 0 has made the system stable. So this is another point. I loosely say that LHP zeros in the loop gain can make the closed loop system stable. Okay. So now we have some understanding of stability and the related stuff. We have this understanding in frequency domain. So once you know something in frequency domain, it also makes sense to understand in which domain? Time domain, because sometimes understanding or looking at the scenario in the frequency domain is helpful, but sometimes looking at the time domain is more beneficial because the other domain will not give you anything. So this is like, asking pocket money. If you ask your dad for pocket money and if he doesn't give, who do you ask? It's all right. So if frequency domain doesn't work, go to time domain. So in particular, we will try to understand 2 things intuitively. That is, if we add a lot of poles in the system, why the system in closed loop becomes unstable. Secondly, how this act of introducing LHP zeros is improving the stability. So these 2 are 2 broad questions we will try to qualitatively find answer in time domain, right? And for that, let's actually look at what happens when you have poles. So I'll take a simple first order system. Let us say we have something like this, right? Now let us say I feed in a signal, a sinusoidal signal, sine of omega 1t. Right? So what can you say about the steady state output? In the steady state, how do you think the output will look like? Okay, if I feed in a sine wave to this LTI system, at the output what do you get? Sine wave. But what changes to the sine wave? magnitude and phase changes. So what happens to the amplitude? A naught, and then is it just A naught sin omega t or something? Okay, see, this is the, I mean, if, yeah, remember that if I write the frequency response, that is basically you replace S by j omega. So what this says, if you apply a sinusoidal frequency or a complex exponential at a particular frequency omega, this is the scaling factor it imparts to the complex exponential. So here it's omega 1, that's the frequency. So the magnitude is what? This guy. And we also have a change in the phase. And what is the phase? Minus tan inverse of omega 1 by p1. Okay. So now let us say I consider a case where the frequency I look it's smaller than omega 1. Sorry, smaller than p1. Right? So how can I approximate this then? Yeah, I mean, if omega 1 is much smaller than p1, I can approximate it as a naught. So similarly, I have tan inverse of some small number. Tan inverse of a small number is what? Okay, let's not make it so small, right? I mean, tan inverse of x is approximately x, right? I mean, in fact, you can look at it this way. See, if I look at the Bode plot of this, let me draw the frequency response as such. This is the magnitude. So we have this pole. In the Bode approximation, we'll have something like this. But if you sketch the actual frequency response, we'll have something where at the pole frequency, we have 3 dB reduction. Similarly, if I sketch the phase plot, at the pole frequency, what will happen to the phase? No, at the pole frequency, what happens to the phase? If omega is p1, minus 45. Tan inverse of omega 1 by p1, omega 1 is p1. So that goes to minus 45. So this is minus 45. And as I tend the frequency to infinity, okay. So I mean, here you can see, when you consider a frequency equal to the pole frequency, the magnitude scales only by root 2, but you can see significant phase has been added here, right? So typically the effect of the pole is much more visible in the phase domain, I mean in the phase plot than in the magnitude plot, right? So that's why here also you see that the magnitude doesn't change so much, but you will see significant phase. This is in this region, okay? In this region, you see magnitude doesn't change so much, but significant phase has been accumulated already, right? So if I rewrite it, I'll have sine of, I'll take omega 1, right? So in steady state, this is the output I'll have, and what can you say about the output? When you compare it to the input, how does it look like? Yeah, it looks like the output is kind of a delayed version, right? So you have a time delay, and the delay is approximately 1 by p1. I mean, please note that this is only in the steady state, right? Because see, finally you'll apply some input like sine omega 1 t u of t, which is, it will be 0, and then you apply the sine wave. This is the input, right? So when I apply the input suddenly, there will be some transient here in the output, and in steady state we'll have the waveform looking like this, where it looks like a delayed version of the sine. Okay. Here something will happen and it will build up slowly. What we are plotting is just a steady state output. We haven't mentioned anything about transient. When you apply the input suddenly, something will happen. It will slowly build up based on the natural response of the system, and then you will have a case where it looks like the sine wave is delayed by 1 by p1. So essentially, if you add a pole, I can qualitatively say that I am adding a delay in the system, right? So which means if I take, say, this first order system,
So what decides the length of the transient?
What do you think decides?
The pole location, the pole of the
It's a pole, right? See, finally you will have something of the form, you will have, I'm not writing it clearly, but you will have something of the form e power minus p1t times lot of things, right? So the transient dies with this thing. So if you have, depending on the pole location, it will take longer or smaller, right?
The pole is very large, then it will die out.
Oh, that's all. I mean, simplest thing is assume that the pole is at infinity, right? Then this is just nothing. It is just a constant gain, so you'll get the same thing. So zero transient. So if the pole is at a lower frequency, the transient will be longer. So you can compute the Laplace transform and find the transient. That's okay. Not relevant. Yeah. So now let us say I take this first order system and put it in negative feedback, and let's say the feedback is unity feedback. So there is no feedback factor here. So, and let us say I apply a step at the input. So at the input I have made the signal go from 0 to 1. So initially all the outputs are 0, right? So even the error signal here will be 0. Now I instantaneously made the output step to, instantaneously have stepped the input to 1. So nothing changes instantaneously, so everything will be at 0. So error signal will instantaneously jump to 1, right? So if I just look at t equal to 0 plus, it appears as though I applied the step input directly to this first order system, right? Only at t equal to 0 plus, right? So then how do you think the output will change at t equal to 0 plus? It is starting from 0. I have applied a step to this open loop system. So initially how will the output change? Huh? Okay, maybe I'll do this way. Okay, see, I am looking at t equal to 0 plus. Loosely speaking, at t equal to 0 plus, when I say t equal to 0 plus, do you think I am looking at small values of s or very large values of s? Instantaneous change, like very large frequencies. So how can I approximate this transfer function as? I have 1 plus s by p1. I am looking at very large values of s, right? So this is of the form basically something 1 by s, right? And the input I have applied is a unit step. This is the input. The transfer function is what? That is also of the form 1 by s. So the output will be, so how will the time domain waveform look? Ramp. Initially it will rise linearly. Just if I look at the slope at t equal to 0 plus, it will look like a linear thing with the appropriate slope whatever you calculate from this, right? So this will increase linearly. So if this increases, this will fall linearly. So which means the signal or the kick given to the system has reduced. So which means even the slope of this will reduce, and then you will finally have this nice exponential settling.
So step input contains all the frequencies or the higher frequencies?
Step input, so you know what is it, right? I mean, see, this is all I am giving a very qualitative explanation. If you look at the frequency spectrum, you know how the step is going to look like, right? But what I am saying is I am looking at an instantaneous jump. So which means at least qualitatively I am looking at a very large frequency, right? That's all. I am not looking at the frequency spectrum of the input itself. At that instant where I am having an instantaneous jump, loosely speaking, it corresponds to a very large frequency. It's just a qualitative explanation, that's all. Okay. Cool. And of course, as you know, this guy is always stable. So that's why it settles properly. So now let's consider a case where we'll have instability. So what is the minimum order I need to have the closed loop system to be unstable? Second order, do you think it is exactly, is it strictly unstable? If you recollect second order, the root locus, it was just doing this. It never entered the right half of S plane. So we need minimum third order. So let's take a third order case. I'll consider the same thing, just that, oops. Okay. So same scenario. So output is also initially at 0. At t equal to 0 plus, nothing changes instantaneously. It will be like this. So it means, again, at t equal to 0 plus, it is as though I applied the step input directly to this third order system. So once again, at t equal to 0 plus, this I can approximate as 1 by s cube, right? So how will the output go as? Now it is 1 by s power 4. If it's 1 by s, it's going to do this. S square, it's going to ramp. S cube, I mean 1 by s corresponds to a constant. S square is t. S cube is t square. Right? So if I plot, this is, let us say, t. T cube will be rising slower than this or faster than this initially. Initially it will be slower, right? And then it will rise like this later. So here if I plot the output again at t equal to 0 plus, it is going to rise very slowly, right? And qualitatively speaking, when I had one pole, there was some delay. Now I have 3 poles. Delay is higher or lower? Higher, right? So it's taking more time to respond. So now this will also increase, but I will say increases slowly. So this will also increase slowly.
So it increases slowly because of more number of poles.
Yeah. Again, it is the same thing, right? If it was just a 1 by s behavior, it rises instantly. S square, it goes as ramp. That's what happened with the first order system. Here there is t cube behavior, which means initially it's going to rise slowly. So this is going to respond slowly, and it will keep doing this. And ideally, if you reach this point, the error signal will be 0, right? Basically, output is same as the input. The error signal, which is the signal here, which acts as the excitation to the system, that excitation signal is 0. But as you know, the system has more delay. So which means at this instant, it will be responding to some signal applied earlier, right? So which means the system is oblivious to the fact that the output has reached the desired value. So which means it will try to keep increasing the output like this, right? Now after some time it recognizes that, hey, I have exceeded my output. I mean, I exceeded the desired value, so it will try to drop. Now once it drops, it is again late enough, so it will again do this and then keep ringing. That okay? So that is why if we have, now it depends, right? If it's a third order system, if it's unstable, it can keep blowing. If it's stable, eventually it will, eventually it will die out if it's stable. If you have, sorry. It can, yeah, depending on lot of parameters. Again, this is a qualitative explanation. Depending on the things, you can have something like this, or you can also have the same frequency. Yeah.
So even if the system is very late, then also it will rise up and then it will go down. What makes the amplitude rise? What makes it blow up?
If it's more delay, see, a simple example I give is, let us say you are, winter time, you are trying to mix hot water and cold water. You have 2 taps, right? You try to mix hot water first, cold water first, dip your hand in the water and check how the temperature is, and then adjust accordingly. Let us say you're doing it very slow. By the time you sense the temperature, let us say hot water has increased more, so then you will add more cold water. And then this can, if the delay is so much, then you might not reach a steady state, right? See, that's a practical example. Okay. So the bottom line, okay, what happened to the plot? Okay. If you have lot, it depends on A0, right? See, A0 depends on how fast you are rising or slowing, right? If A0 is small, this might be rising even I mean something like this, right? Or I mean what I'm saying is this is scaled. If A0 is large, it will do this.
So A0 is large, we have more chances of becoming the output being unstable.
Yeah. Because A0 is large, you will overshoot a lot, right? A0 is just the gain. So for the same input, if A0 is large, you will overshoot so much. That is like saying the tap water, I mean in the water analogy, you increase the inflow and outflow of the water, right? You sense temperature, then you increase the, hot water more. So temperature will increase even faster, right? So bottom line, if you have LHP zeros, it introduces time delay, and anytime you have a delay in any kind of feedback loop, that can result in instability. Oh, sorry. Thanks. Yeah. Left half plane poles. Thank you. Yeah. Okay. Cool. So this at least clear now why the poles are making it go unstable. Now let's try to get the answer to the question as to why when we have left half plane 0 things are becoming stable. For that, first let me take a look at the same thing. I'll do the same exercise, just that I'll take a 0 now. So this is now, I'll erase this, not needed. So if I do this, what will happen to the steady state amplitude? This is the system. What is the sinusoidal magnitude in steady state? Yeah. So it's A0 into same thing. And what happens to the phase? So as usual, if I use this condition that the frequency of the sinusoid is much smaller than the pole location, actually I'll make it clear, this is 0, so that there is no confusion. If I consider a case where the input sinusoid is at a frequency much lower than the 0 frequency, how can I approximate this as? You'll have the same thing. Right? So if I do this, I have, so what do you have now effectively? If I apply a sinusoid like this, at the output I seem to get something like this. So what have I incurred? Yeah, I mean it's basically a time advance, right? Okay, so looks like this is a great way to look into the future, right? Why don't I use it to build a time machine?
This is not like you cannot build this type of system which is 1 0.
Okay, that is okay. Practical. Okay, let us say you can even do that. Yeah, that is true. It might not. You can't have a system only with a 0, but let us say I can also have 1 plus s by p1, and I can have, let us say, time advance greater than the time delay. Right.
Causality, like.
Yeah, but this system is causal. Okay, see, when I write this, I apply a input like this. This is essentially what kind of output is this? This is the output for all time, or I am looking at some specific time? In steady state. Okay. So what happens is, I mean, if you apply some input like this is the input. It is not as though the output starts coming like this, right? This is basically the time machine where you have non-causal system, but it doesn't happen. You have some transient here that I'm not sketching. So here you'll have some transient, and in steady state you will have some scenario like this. That's what happens, right? And it can understand how this happens with a circuit example. So let me take this first order case. So if I apply a unit step here, let us say this is R1 C1, the out. How will the output look like? This is the input. How will the output rise? Yeah, it will basically rise. You guys know this already. Okay. So how many poles and zeros the system has? One pole and there is no zero. Now let us say I go and put a capacitor across this guy. Say this is C2. Now how many poles we have now? One pole, because if you again to find the poles you short the input and you see these two capacitors are in parallel. With just one independent state variable you can initialize. Do we have a zero in the circuit? Yes. Yeah, you can basically short this capacitor. Still the output is non-zero. And even qualitatively speaking, I have currents from two different branches getting added up. They will have different phase shifts. So at some complex frequency we'll have the zero. Okay. So it's a first order system again, but with a zero. So now help me sketch the step response.
Initially it will like start with.
Okay. Let's probably let's start that. For first order system, what are the three things I need to sketch the step response?
Initial, final and time.
Yeah, initial, final and time constant. What is the final value here? I mean, as t tends to infinity, what can you say about the capacitors? So what will happen to the output?
1.
So I'll say v of infinity is 1, right? And time constant, what is the time constant? I short the input. What is the effective capacitance I have? What is the time constant then? Right? So now only thing pending is 0 plus. Yeah, what is that?
It's 1 times C2 1 C2.
Yeah, why?
Capacitor division. Like they will offer very low impedance.
See,
So I can
okay, when I didn't have this, did the output change instantaneously? Why didn't it change instantaneously? Yeah, resistance is there, so? Okay, let me. Why didn't the output here change instantaneously? So? Yeah, it's all correct, but why? Sorry? Okay, if the capacitor voltage has to change instantaneously, how should be the current? So in this case, the impulse current can only flow here, which means the voltage across the resistor has to be some impulse. But nowhere in the circuit we have impulsive, voltages. Everything is a step. So simply you can contradict that. That's not possible. But the moment I put this capacitor, if we want this impulsive current to flow through this capacitor, it cannot flow through the resistor. But is there some other path it can flow to? We can. Now if impulsive current flows through both capacitors, both voltage change as a step. Everywhere you have step voltages, everyone is happy, right? So at t equal to 0 plus, only this capacitor conducts the current, that is the impulse current. So I can redraw the circuit like this. So what will be the output at t equal to 0 plus? It's a capacitive division, so it will jump up instantaneously to say C2 by C1 plus C2. And then what will happen? And then it will basically exponentially settle. Fine. So now you see, right? The moment you added this LHP 0 here, the output has jumped up in the same direction as it has to settle. So that is the kind of time advance the 0 is giving us. It is not as though the output has started to exponentially rise like this. If this happens, that is a non-causal system. But what happens is the LHP 0 is causing the output to jump up in the same direction as you want the final output to reach. That way the settling could be faster. Right? So in short, if you have an LHP 0, it introduces some kind of time advance. and that time advance, it counters the time delay added by the pole. The pole is adding a time delay. If you have a 0, by making sure the output jumps up or down in the correct direction, it introduces an advance. So overall delay in the loop will reduce, and that's how the system becomes stable. Is that okay? So I'll just say time advance counters the time delay from pole.
Time t equal to 0 plus capacitor will be shorted.
Yeah, that is correct. I mean, see, there are fine points, right? Okay, I understand what you are getting at. So his question is, yeah, first you think why is that true? His question is at t equal to 0 plus, you might have learned capacitor acts like a short circuit. So why is the output jumping instantaneously? Why? Yeah, that is one thing. Impulse current is flowing, and even otherwise, right? I mean, this is basically acting like a short circuit or a very low impedance. So if I put these two in parallel, is the case. Now we have two low impedances like this. So it will be a division between those two impedances, right? You can think of it like this. It has some Z1, Z2, where both of these two tend to 0. But one of them will tend faster to 0 than the other, right? Because capacitor impedance is 1 by SC1, 1 by SC2, right? Depending on which is offering a lower short circuit than the other, you will have a division. That's all. Cool. So this is how, I mean, this is why the LHP 0 is helping in stability, and that we saw in the frequency domain from the root locus plot also. So if you don't have the zeros, the poles could actually enter the right half of S-plane, but the zeros are attracting the poles and making them fall not just in the left half of S-plane but also on the real axis. Right? Cool. So now that we have seen LHP zeros, let's also look at RHP zeros. So again, I don't want to do the calculations again. Let's see if I can copy this. Right. So it's an RHP 0, so I have 1 minus S by Z1. So what changes here? In this expression, what changes? The delay, I mean the phase becomes minus. So again, if I tend this condition, I can approximate as A0 times sine of omega 1 t minus 1 by 0. So this RHP 0 is introducing what? Yeah. This is giving a time delay. So this is good or bad? This is bad for stability because it introduces more and more delay in the feedback loop. And once again, to understand an idea, to get an idea as to how this delay is adding or getting added, let's look at a circuit. I'll take the same RC. The only difference is I'll do this. Okay. This is basically a buffer with a gain of minus 1, right? So you can work out and find that this introduces an RHP 0. So here, let me label this. So if I apply an input step at t equal to 0 plus, what will happen to the output? Yeah, voltage division. So what? Again, same thing, right? I mean, you have C2 and R1 in parallel. Which of the two will dominate at t equal to 0 plus? C2. So R1 I can ignore it. So I can redraw the circuit like this. Yeah, exactly. So if you will have something like this. So you're no longer applying the step u of t. You are applying what? Minus u of t. So the output, it jumps to that value of whatever, minus C2 by C1 plus C2, and then it will slowly exponentially rise. If I didn't have that RHP 0, it would have nicely done this. Now it takes more time. So RHP 0 will cause the output to jump instantaneously, but that jump will happen in the opposite direction to where you want your final output to reach. That's how it introduces more delay. So you can actually show that if you have n 0, at t equal to 0 plus, you will have this kind of a jump. And if it's an LHP 0, it will jump in the right direction. If it's an RHP 0, it will jump in the opposite direction. Okay. So if you have a step input, you will have this kind of jumps.